period t is equals to 2 pi over omega. Therefore, making omega the subject of the formula, we have 2 pi over t, which is equals to 2 pi over 2 is equals to pi per seconds. Velocity v is a maximum at the equilibrium position where x is 0, and plus or minus omega square root of r squared minus s squared, where r is the amplitude. Therefore, plus and minus omega square root of r, which is equal to plus and minus pi square root of 25, which is equal to plus or minus 16 cm per seconds. Maximum velocity v of the bulb is plus minus 16 cm per seconds. B. Acceleration a is maximum at the limit of the swing, where x is r is equals to plus minus 5 cm and a equals to minus omega squared r. Therefore, maximum acceleration a max is equals to minus omega squared times 5 cm per seconds is equals to minus pi squared times 5 equals to 50 cm per seconds. Example 2. Compute the acceleration due to gravity at a place where a simple pendulum 1.59 meter long makes 100 vibrations in 246 seconds. Solution. Period t is equals to 246 seconds over 100, which will give us 2.46 seconds, where t is the time to make a complete circle, but t is equals to 2 pi square root of 1 over g. Therefore, t squared is equals to 4 pi squared 1 over g. Therefore, g equals to 4 pi squared 1 over t squared, which is equals to, in bracket, 4 pi squared times 1.5 meters over, in bracket, 2.46 squared, which we now have 9.79 meters per second squared. Example 3. A steel strip clamped at one end vibrates with a frequency of 20 Hz and an amplitude of 5 mm at the free end, where a small mass of 2 grams is positioned. Calculate the maximum kinetic energy Ke and the potential energy Pe of the mass. Solution. Apply Ke equals to half m omega squared r squared, where omega is the angular velocity and r is the amplitude, but omega is 2 pi f, which is equals to 2 pi times 20. R is equals to 0.005 meters and m equals to 2 grams, which is equals to 0.002 kilogram. Therefore, maximum kinetic energy is equals to 1/2 of m omega squared r, which is equals to half times 0.002 times, in bracket, 0.005 squared, which times, in bracket, 2 pi times 20 all squared, which is equals to 0.0003951 joule, or 3.9 times 10 raised to the power minus 4 joule. Maximum Pe, in bracket, V minus 0 is equals to maximum Ke is equals to 3.9 times 10 raised to the power minus 4 joules. Example 4. A mass of 1 kilogram is placed on a horizontal platform, which vibrates up and down with simple harmonic motion with a frequency of 4 Hz and amplitude of 5 cm. Calculate the maximum and minimum value of the kinetic of the mass. Solution. Maximum velocity in simple harmonic motion, if r is the amplitude, which is equal to 0.05 meters, is given by the maximum velocity Vm is equals to omega r, which is replacing omega with 2 pi f times r, the amplitude, which we now have 2 pi times, we are given frequency as 4, and then times by our amplitude, which is 0.05, which we now have our maximum velocity to be 0.4 pi meters per second. Maximum kinetic energy is equal to half mv squared, or half m maximum velocity squared, which we now get half times 1 times, which is the mass, times 0.4 pi squared. Maximum kinetic energy is so therefore 0.8 joules approximately. Example 5. The length of a simple pendulum is 0.36 meters and it is released at an angle of 10 degrees to the vertical. Calculate A, the frequency of vibration, B, speed when the pendulum ball passes through the lowest point of the swing, given that 6 degrees is equals to 0.1044 radians. Solution. A. Since the maximum angular displacement is less than 15 degrees, we can compute the frequency f as follows. F equals to 1 over capital T, that is the period. Then substituting the period inside, we have half pi in bracket square root of 1 over g, which we now get by putting in the values. We have 1 over 2 pi square root of 10 over 0.36, which will now give us 0.83 hours. B. Since the motion of essentially simple harmonic motion, then V mass, that is maximum velocity, is equal to amplitude times the angular velocity omega, which we now have K, that is kinetic F over M. We now substitute the value, have mg over ml in bracket 0.1974, where the effective spring constant K is equal to mg over L. We now have square root of 10 over 0.36 times 0.174, which will now give us 0.33 meters per second. Example 6. A simple pendulum has a period of T of 4.2 seconds. When the pendulum is shortened by 1 meter, the period becomes 3.7 seconds. Calculate 1. The original length of the pendulum. Solution. We are given that a period capital T is equal to 4.2 seconds and the length, normal length, is equal to capital L. The formula for the period is equal to 2 pi square root of 1 over g, L over g, closing brackets. Then replacing the unknown values, we have 4.2, which is our period, equals to 2 pi square root of the length L over g. This will now become our equation 1. The period after the length is shortened by 1 is 3.7 seconds. The length is shortened by 1, therefore the length will be L minus 1. Replacing the unknown values, we have T equal to, we have the formula for period T equals to 2 pi square root of length over g. Then replacing the values, we have that the period T is equal to 3.